The speed changes, the kinetic energy changes for a particular mass. You might call this the energy of speed, energy of motion, thus the term kinetic. Now, this doesn't really suit physicists. So what they decided was, well, we need to come up with something so we get a conservation law. So what they did is they broke forces up into two types. There are conservative forces and somebody just said it. Non-conservative. They are not limited. Why do you suppose some forces are called conservative? Conserve what?
Energy.
Yes. Conservative forces conserve energy. It's as simple as that. Now, I'm going to list all the conservative forces we have dealt with up till now. There is a formal calculus-based definition, but I think just the list of all the conservative forces works better. Gravitational force. Done. That includes weight. Gravitational forces are conservative. Now, other conservative forces that we will deal with, the ideal elastic force, we will deal with it eventually. Ideal elastic force. And in next semester, in the 152, electric force and magnetic forces are also conservative. Non-conservative, all the rest. Now, non-conservative forces create non-conservative work. So we can, of course, write that notationally, because who doesn't want to write it in shorthand? Work non-conservative is equal to the non-conservative force times displacement. What do you suppose is not conserved with a non-conservative work?
Force.
Somebody just said it very quietly.
Force. Oh,
Energy. So work non-conservative is equal to the change in energy. Well, energy, we have two types. We have kinetic energy and then
potential.
so this would just be the change in kinetic plus potential. Now the symbol for potential energy is a capital U. Some textbooks will use PE. I don't know where they get that stuff from, but capital U. I assume it's from the German.
U makes less sense than the P.
I think that was the joke.
We use P for momentum. And so if you went PE, now you're just writing extra letters and you can't have that.
Okay.
That would just be silly.
Right.
Silly.
So that's equal to the change in kinetic plus the change in potential energy. The change in kinetic energy is the total work. So the non-conservative work is equal to the total work, net, plus the change in potential energy. Let's sort of move stuff around. I'm going to move delta U over to the left side and non-conservative work over to the right side. So I have negative delta U is equal to the total work minus the non-conservative work. And what do you suppose if I take the total work and so take out the non-conservative work, what am I left with? Yes. That's equal to conservative work. Because I have only two types of forces, it's either conservative or non-conservative. The total force would have to be the non-conservative forces plus the conservative forces. Work equal to each other. So what we have are three work energy relationships. We have the thing that's called work energy theorem. We have non-conservative work is equal to the change in total energy, I guess mechanical energy. And the conservative work is equal to the negative change in potential energy. getting ready to ask you the question again. What's the formula for kinetic energy?
1/2 mv squared.
I think that takes away from the chorus of angels.
Yeah.
What's the formula for potential energy?
The same.
No, it is not.
Alright.
Now, the proper response, I was just wondering if someone who's had physics before was going to chime in with AGH or something like that. The proper response to what is the formula for potential energy is which one? What's the formula for potential energy?
Which one?
That was less a chorus of angels, seemed to be a little bit quiet in the back, that could be just I'm too far away.
Ask again.
What's the formula for potential energy?
Which
Which
one?
Not necessarily the angels, but that was definitely a chorus. So, the reason why is that every conservative force has its potential energy formula. Some of which I'll derive at least one of them, some of which I'm not going to derive and you just have to take it on faith. So if the conservative force is the generalized gravitational force, so here's the conservative force, here's the potential energy formula. The formula is negative big G mass 1 mass 2 over R. It looks a lot like the gravitational force formula, but I'm missing the R on the bottom. At some point, when dealing with gravitational potential energy, I will write R squared out of habit. You are to correct me before I go too far. If we are talking about weight as the gravitational force, or mg, if we're talking about a region where little g is relatively constant, then the formula is mgh, actually, plus some constant. If we're talking about an ideal spring, or an ideal elastic force, I don't use a subscript E for elastic because I saved that for electric in the next course. This is a spring force. It is 1/2 little k delta x squared. Little k is known as the spring constant. And delta x is a shift off of equilibrium. How much has the spring been stretched or compressed from equilibrium?
That's little k you said?
That's a little k.
What is the underscore next to the F, the force,
Wait,
in the
wait.
left, at the top?
F, that's a C for conservative.
Spring what?
Constant. Now, it's said that people with MDs are supposed to have the electrical handwriting, but I think I should be extended the same courtesy. So the claim is that if there's a conservative force if there's only conservative forces acting on an object, then energy is conserved. So we can also define conservative forces as not only conserving energy, but conservative force changes energy from one form to another. Changes energy from one form to another. Non-conservative forces transfer energy from one object to another. Non-conservative force transfers energy from one object to another. So if I drop a book, ignoring air resistance, while it is falling, the kinetic energy is being, the potential energy is being transferred to kinetic energy. You start out with all this potential energy. As it falls, the total stays the same. As soon as it hits the ground, we've introduced a non-conservative force, it's a normal force. As soon as it hits the ground, energy is transferred into, well, here, the carpet. The carpet and the bullet actually, it'll get distributed among both, but they will heat up a little bit. I don't know if you've seen the video of the person heating up chicken by slapping it.
Oh, yeah.
It-
Seen the copy.
We eventually got to the point where you could actually eat it without getting sick, but,
Nah.
Yeah.
They were just by slapping it?
yeah, he developed a machine that.
Oh, yeah, that's right.
He just sat there and
That's what I thought. I was like, that
I mean,
would
at some
take
point.
so long.
Yeah, it did. Especially with all the failed trials as well. The first one, he did not, he eventually had to enclose it because the heat that was generated was, a lot of it was dissipating. And so it took a while, but eventually.
How did it not break, like fall apart? You know what, I'll watch the video.
Yeah, how did we come up with this
I- I-
experiment?
I forget that part, but anyway. So that's the basics right there, the rest is just, math and interpretation.
Okay, can you elaborate more on, the spring force, conservative force, and its relation to the potential energy equations that you're
Every conservative force has a potential energy formula.
Okay.
So that's why when I ask what's the formula for potential energy, the response is which one? Because I've got, here's 3 of them right here, there's gonna be more next semester.
Okay.
Yes, that's the right attitude. Next course, whatever, next quarter,
Next section?
sure,
So physics two,
yes,
okay.
that's probably the shorter way of saying it. Questions right now?
So spring force is also conservative?
Pardon?
Spring force is also conservative?
I missed,
Is spring force a concern?
yes, the ideal elastic spring force.
Oh, that's the same.
Elastic and spring, throw it together. All right, let's transition into class. Some of you don't have a copy yet. I'm gonna have to go get the equipment.